Welcome to the feed talk of this week that will be given by Johanna Mayer, who is a research fellow in the Science Hub, researching in the Science Hub at ESA at Eswin. So she's a colleague of ours, and she's researching cloud structures, mainly using the EarthCARE satellite, and she will present her latest project, of which she will give you the further introduction herself. So please, Johanna, we are listening.
Yeah, thank you, Ruben, and yeah, thanks for the invitation. I'm happy to give this talk. So yeah, as Ruben said, I'm Johanna Mayer from the ESA Science Hub, and I work on clouds and specifically with the EarthCARE satellite. And this talk will be about cloud structures and especially about closed and open cells. And I'll explain later what exactly I mean by this. So to give you a bit of an outline, here's what I will talk about. First, I'll try to convince you that Stratocumulus clouds and also closed and open cells are important. Then I'll give a brief introduction to the EarthCARE satellite. I'll show how we use machine learning for cloud structure detection. And then sort of the main part is point 4, where I'll show the results of this study. So I'll show properties of closed and open cells and what happens around transitions between these cloud structures. So first of all, why do we care about clouds? From a climate perspective, clouds are really important because they impact the Earth's radiation budget. So clouds reflect part of the incoming solar radiation, which means they have a cooling effect on Earth, but they can also trap heat, outgoing long-wave radiation that's emitted by the Earth. And then sort of which of these two, the cooling or the warming effect, dominates really depends on the cloud properties. And so if we want to know how will our climate change in the future, we really need to get the clouds right. So what's shown here is a figure from the IPCC report and the different colored lines or different emission scenarios. And I want to draw your attention here to this this background, which shows the uncertainty of these estimates. And the uncertainty is quite large. And the uncertainty actually comes mainly from clouds. So some models represent them differently than others, and we don't have we don't know exactly how clouds will change as we change our atmosphere. And this then has feedbacks on if we will get more or less warming. Now, the clouds that I will talk about are subtropical stratocumulus clouds. They're shown here in this snapshot, and they're found in different regions of the Earth. So always sort of at the eastern part of large oceans. So here, for example, is the Stratocumulus cloud deck of the Southeast Pacific. And these clouds are really low level, so they have a really low altitude. Hope you can read it kind of. And the important thing from from this radiation perspective is that they have a really large extent horizontally, and they're very persistent. So sort of any time that you look at a satellite image, you will find these cloud decks. So they reflect a lot of incoming solar radiation and have a large cooling effect on our Earth. Now, to zoom in a bit to these clouds, this now shows a different Stratocumulus deck near the coast of Namibia. And you can see in this picture already that we have really different mesoscale structures. So with mesoscale, I mean sort of as horizontal scales between a kilometer and hundreds of kilometers. So here more on the right, we have what we call closed mesoscale convective cells, so where you have these closed cloud decks, and you can see the cellular structure in there. Then here more towards the left, we have open cells. So these are sort of the characteristic is this honeycomb-like structure. And then there's more structures like here we have solid stratus, more disorganized cells, or more cumuliform clouds. But yeah, the ones that I'll focus on in this talk are these closed and open cells. And as you can already guess from the picture, the closed cells have a larger cooling effect than the open cells, just because their cloud fraction is larger. And for the open cells, you can kind of see the ocean underneath. So yeah, as you can imagine, when closed cells transition and change to being open cells, this will have an effect on the cooling effect of these clouds. So the question is, yeah, what leads to transitions between these cloud types? And for this, EarthCARE can help. So EarthCARE is a joint ESA and JAXA satellite mission. It was launched in May 2024, and it was built to measure clouds, precipitation, aerosol, and radiation. And it does this using 4 instruments. So first of all, we have the cloud profiling radar here on the top left. And this radar is really good at measuring large cloud particles and precipitation. And it also has droplet capabilities. So it can give us an estimate of how fast are particles moving up or down. And as you see, it gives us, this sort of profile through clouds. Then we have the atmospheric LiDAR, ATLID, which is really good at measuring small cloud particles and aerosols and can give us good estimates about what's going on at cloud top height. Then the third one here is the multi-spectral imager, which measures radiation at different wavelengths in the visible and infrared. And it gives sort of the spatial context to what CPR and ATLID are measuring and can also give us estimates of sort of vertically integrated values. And then the fourth one is the broadband radiometer, which measures radiation, which I have not been using so far in the study, but just to give you all instruments here. So I'm using the first 3 of these instruments on EarthCARE. And yeah, one strength of EarthCARE is that it has these multiple instruments. So from the synergy, because some instruments measure, I don't know, for example, precipitation very well, and then ATLID measures the cloud type very well. And then the synergy can give us a really detailed view of clouds and aerosols, plus the spatial context that we get from the imager, like in the horizontal. So let's take a look at one example orbit. Now this shows an example of Stratocumulus measurements. The upper panel shows the ACM CAP product, which is a synergistic product of these 3 instruments. And we can see profiles of clouds. And then color is shown the liquid water content. And then hopefully you can see it sort of in the background, there's a bit of blue. So this is the rainwater content. And these are, these profiles through the clouds. And you can also see here when you look at the Y scale that these clouds are really at low altitude. So here between 1 and 2 kilometers height, which for clouds is really super low. And then the lower image shows from MSI liquid water path. So this is now the horizontal top view. And where you see this dashed line, this is where the EarthCARE track, so nadir track is, and where we measured the this profile. And from MSI, we get really nice estimates of, or you can see already how different the cloud structures are only around this track here. Then some points why I think EarthCARE is really good also for, especially this problem for low-level clouds, are that EarthCARE has a higher horizontal and vertical resolution compared to previous satellite missions, so which can be important, especially for these small clouds. And we have reduced surface clutter contamination. So surface clutter means that when the radar, or especially this is a problem for the radar, like when the surface has strong returns, then it can contaminate sort of your low-level cloud measurements. And for EarthCARE, this seems to be working really well. And then the CPR instrument is also more sensitive than sort of the predecessor CloudSat. Has been shown that it enables the detection of double the amount of stratocumulus clouds and also weak drizzle and small raindrops. And last but not least, the Doppler capabilities can be really useful in these retrievals because they help us to better constrain raindrop size. Because if we know how fast particles are falling, for example, this is really well connected to the particle size. So we have an additional constraint. Now, if we want to study cloud structures, we need to be able to detect them. And this is now where, sort of the machine learning part of our work comes in. So we used a convolutional neural network to detect different cloud or to classify different cloud structures with the backbone BreathNet 50. So this neural network was originally developed by Wu et al. In 2025, and it uses scenes of 128 times 128 kilometers from an imager in 3 infrared window channels and plus cloud optical depth. So sort of here, these 4 inputs. And then as an output, it gives us one of 6 different cloud structure classes, as well as a probability or like a certainty estimate. And as I said, I'm focusing here on closed and open cells. So 2 of these cloud structures. And because this original neural network was created for MODIS, so different imager, I fine-tuned it to EarthCARE to increase the performance, and also to GOES-ABI, but I'll go into detail why I also applied it to GOES later. So because we're in the Phi-Lab, I thought I'd give you some more details about the fine-tuning. We only fine-tuned the final network layer and using some manually labeled cloud scenes. Also, because the original resolution that the network was trained on is 1 kilometer, and EarthCARE has actually a finer resolution, first coarsened to this original resolution to apply the neural network, and used manually labeled around 500 scenes. And the nice thing was after the fine-tuning step, we saw that the neural network really shows substantial improvement in the classification skill. So here, for example, is shown the confusion matrix when the original model was applied to the manually labeled dataset. And then here is sort of after fine-tuning, we see that the accuracy improved, especially actually for here open cells, and also the F1 score for closed and open cells looks quite good. So now here, this shows some example pictures of this classification. So these are 3 different orbits from EarthCARE MSI, so from the imager. This square here shows the window size, and the colored dots are the classification of the neural network. And here in blue are shown closed cells, and in orange open cells. So just to sort of get a feeling about the sizes and how the neural network works. So in general, from I don't know, in just manual inspection, it seems to work quite nicely, even though sometimes, like here, for example, I might have put closed cells like myself, but sometimes it's a really difficult call because of course these cloud classes, they're not actually classes, but the spectrum between each of these classes. So sometimes it's really difficult to classify. But in general, we're quite happy with the performance, I would say. So then we applied the neural network on EarthCARE data of about 15 months in 4 typical Stratocumulus regions that are here shown in color. And what's shown here is the frequency of occurrence of closed cells in the upper one and open cells in the lower plot. And what we see here from the geographic distribution is sort of what we would expect. So this is also again a bit of a check if the neural network is doing a good job, because we would expect closed cells being more towards the east and then open cells a little bit more towards the west. And this seems to be the case. So that's nice. Now, with this sort of labeled, or classified data set of about 15 months, we then did some statistics first of all. So looking at the properties of closed and open cells. So here are again some examples to get a feeling of what these clouds look like in MSI and in ACM CAP. So shown here is for the upper one shows closed cells in the horizontal view, and then the upper plot here shows the profile of these closed cells, and here shown is liquid water path and liquid water content, respectively, and here the same for open cells. So we can see already sort of that in the vertical, or maybe that. Yeah, maybe I'll just show the statistics first. So this is the statistics of all the data that we have. So this is about always taking sort of the mean of these 128 kilometer boxes in ACM CAP, so always along track. And we see here that for closed and open cells, on the average, liquid water path actually looks quite similar. What's not shown here in the statistics, but if we look at the variation, for example, of liquid water path, we see that open cells have much larger variation, which we can also see here in these examples. So we have some places where we have much higher liquid water content, and then some places where we have really thin clouds with really low liquid water contents. Next, looking at effective radius, so how large are droplets? We see again that sort of in the mean, it looks quite similar. But again, for open cells, we see a much larger variations in effective radii. And lastly, here shown is the number concentration. So how many droplets do we have in the clouds? And there we can also in the mean see a really large difference between the two cloud types, with open cells having much lower number concentrations.
Exactly.
Last thing about these statistics, here shown the rain properties of both cloud types. First of all, looking at the first plot in the statistics, the rain occurrence is higher for open cells. However, it's maybe not as much higher as you would expect from the literature. And because we even see around 60% of closed cells that precipitate, which is something that we maybe didn't expect to see. However, this precipitation in closed cells is often very light drizzle, which is shown here in the rainwater path. Yeah, and I think this is due to this new sort of very high sensitivity of EarthCARE, that we can detect even such low drizzle values. But overall, to summarize sort of these statistics, we see that open and closed cells show quite some significant differences in their microphysical properties. So we have lower droplet number concentrations and higher rain rates in open cells. So this might already maybe give us a hint that microphysics is important for the transition from one cloud type to the other, because as we can maybe also see here in these examples, like in the vertical, on average, it sort of stays quite similar. So open cells are not for example, they don't have much higher cloud top heights. So I mentioned here that we see, on average, relatively similar liquid water paths, but higher rainwater paths in open cells. So this sort of means that apparently the production of rain is much more efficient in open cells. And this is what's shown here. So in the left plot, we see the liquid water path against rainwater path and the y-axis. And we see that for the same amount of liquid water path, open cells rain much more. And I checked, and it seems that this higher rainwater path comes mainly from the fact that droplet sizes, like raindrop sizes, are much higher in open cells compared to closed cells. So it's not about the number concentration, for example, but about they accumulate somehow to much larger raindrop sizes. Now, I told you that the main objective of this work is sort of to understand why transitions from closed to open cells happen. And in order to understand this, we sort of needed to also get the time information in there. Because with EarthCARE, of course, it's a polar orbiting satellite. We always have just a snapshot view. So to do this, we also added geostationary data for the Southeast Pacific region, so using GOES data. And this is what's shown here. So in this movie, the left one shows cloud optical depth from GOES, and the right one shows brightness temperature at an atmospheric window channel, just to sort of see also, because now it's night, and then we don't really have information about the cloud optical depth on the right, on the left. So the right one also sort of shows us what's going on during the night. And these dots that are moving, these are the these are the cloud scenes that are tracked using ERA5 wind data. And the colors are, the classification of the neural network that we also applied to GOES for, again, made like a fine tuning of the neural network to then be also able to apply to this geostationary data. We can see here, for example, how these, there are some open cells forming here that then grow in time. Yeah, so now with this time information, we can, track the clouds that EarthCARE has measured backward and forward and see whether a cloud that was measured by EarthCARE shows a transition from a closed to an open cell or not. And in the following, I filtered only for the clouds where we see a transition happening. So these plots now show all the transitions that I found in this like sort of 15 months of data. Here, the left one shows that transitions are mainly found during the summer and autumn months, and here the right plot shows the trajectories of the clouds for which transitions were found. So the dots here show where the position of the clouds at the EarthCARE overpass, and then sort of the line, and then where the cross is shows where the cloud transitioned here in this left plot from a closed cell to an open cell, and then the right plot the other way around. Sort of, it was first when EarthCARE measured it, it was already an open cell, but we could track it back to when it was still a closed cell. And then, so from sort of combining this information from GOES about the time evolution together with EarthCARE, then can look sort of like this. So here for this example in yellow, we see that at the time of the EarthCARE overpass, it was still a closed cell. And then from GOES, we can get the information that here, about 1 hour later, it will transition to an open cell. And then from EarthCARE, we can get all sorts of microphysical information about this cloud. So here shown is, for example, the rainwater path. Or here, another example, these clouds were already open cells when EarthCARE overpassed them, and we see in the time information that about 3 hours earlier they were closed cells. And again, we can check what was their rainwater path in EarthCARE. So doing this for all the transitions that we found, we can do plots like these. So here, yeah, for each time to transition value, we can get from yeah, all these around 800 transitions that we found, the corresponding EarthCARE values. So here shown is the cloud cover on the right, with these dashed lines that you see here in the background. They are the climatological mean. And then we can sort of, yeah, we can check how cloud properties change around transitions on average. So this here shows that the cloud cover sort of does as we would expect. While the clouds are still closed cells, the cloud cover is really high at values around 1. And then as soon as they transition to open cells, it drops really fast and is then at much lower values around maybe 0.6, 0.7. Now let's check some more values. So here shown is are some microphysical quantities as a function of time to transition. And there we can see some really interesting behavior around the transitions. So first of all, here, liquid water path, we see that it increases before the transition, and it actually starts quite early to increase, so around 25 hours before the transition. Also, rainwater path has a strong increase, and also that one already increases around 25 hours before the transition. Effective radius starts to increase a bit later, maybe, I don't know, 18 hours before transition, and then shows this drop when the transition is happening, also for liquid water path, in fact. So this drop is sort of when we see optically really thin clouds forming in between these thicker open cell structures. And then lastly, for number concentration, we also see a decrease starting around 20 hours before a transition. Now, because an increase in rainwater path can come from, yeah, sort of many different things, I looked at this a bit more closely, which is shown here. So this rainwater path is this average over 128 kilometers, right? And also an average or a sum over the vertical. So the increase in rainwater path can come from differences in rain fraction. And we see that rain fraction here on the left is really much higher than the climatological values for clouds that show a transition. And also here, this shows the rainwater path below cloud. So sort of how much rain, yeah, sort of how deeply rain can penetrate below cloud, because very often the rain in these clouds, a lot of it evaporates. So also this already starts to increase fairly early. And then actually the rainwater content, so which means sort of the amount, how much is the cloud raining inside the cloud, only starts to increase a bit later. So maybe this is now all a bit cryptic. And what does this all mean? So here I try to like combine all this information to form sort of a timeline about what's happening physically around these close to open cell transitions. So I think what the data that I just showed you suggests is that the initial trigger for a transition may be increased moisture in the boundary layer, because we saw that the first things to increase were liquid water path, which depends on the moisture, and also the rain fraction and rain below cloud. Yeah, so this increased moisture might leads then to increased liquid water path, rain fraction, and rain below cloud. What I said around, yeah, these 25 hours before transition. When rain starts to reach the ocean surface, there's sort of there's another thing starting to happen which we cannot measure here directly, but we know that rain scavenges aerosol. So there's aerosol in the air and inside each cloud droplet, and when it reaches the surface, sort of the aerosol goes into the ocean and is kind of flushed from this system. So as soon as when we have enough rain that it reaches the surface, we get aerosol scavenging. This then, when we have less aerosol in the boundary layer, this leads to lower number concentration and larger radii of cloud droplets. So you can imagine, in each cloud droplet, there's at least one aerosol. And if we have less aerosol, we will have less cloud droplets. But if we still have the same moisture available, the cloud droplets will just grow larger. And when we have larger droplets, we also, again, increase the rain. So what we get is this sort of feedback mechanisms. With more rain, we get more aerosol scavenging, we get lower number concentrations and greater, higher radii, which again leads to more rain, and so on and so on. And then in the end, what might lead to the transition, for this, really the dynamics of clouds to change, is the evaporation below clouds. So when we have a lot of rain and a large part of that evaporates, it cools the air a lot, which leads to sort of sinking air, which then when it hits the surface, it spreads out. And when we have two of these cold pools, or actually three usually interacting, then you can imagine that it sort of pushes air up again. And this is then sort of a change in the whole dynamics of the clouds, which can lead to this open cell structure. This is also not, it's not my ideas that are in here, but this cold pool hypothesis has been in the literature for some years and was already shown in LES studies, for example, to work. But I think with EarthCARE, and especially combined with geostationary satellites, it's nice that we can sort of get this really detailed timeline of when things are happening. And then draw conclusions like these about the physical processes. And then I'll just finish with this sort of last picture. This here shows, on the left-hand side, we see a GOES image of mainly open cells. So a situation like this, where open cells reach so much towards the east, is quite rare, but sometimes it happens. And then on the right, this shows the Sentinel-1 picture. So a polarization measurement. And as far as my limited understanding in terms of Sentinel-1 goes, this can sort of measure the ocean roughness, and with that, sort of the winds on the ocean, the wind speeds. And as you can see here, we have these sort of, these round blobs, which are cold pools that you can see on the ocean surface. So so air spreading out radially. And they coincide here with these open cells. So of course, this does not mean that they are really responsible for the cloud breakup, but it sort of gives another piece to the puzzle, and it shows that there are cold pools happening below open cells. And with that, thank you.